All right, let's take a look at the third law of thermodynamics. The first law of thermodynamics is basically the conservation of energy. Okay. The second law is about spontaneity. It tells us what processes are and are not able to happen under their own powers. Those are two serious and important ideas. The third law is a bit less momentous. Really, it's just a way of keeping score on entropy. Okay. So what do we know about entropy? We know the entropy of any material increases if the temperature goes up, right? So anything I take, if I raise the temperature of it, its entropy should go up. As I lower the temperature, molecular motion will diminish, right? And so because there's a hypothetical limit to how far I can lower the temperature, and that would be 0 Kelvin, that says there's a hypothetical limit to how far I could lower the entropy. Okay, so the third law of thermodynamics says in words, the entropy of a pure perfect crystal of any material at 0 Kelvin is 0. Okay, so what that does is it establishes a scale for entropy values, and it gives us a way to actually measure and talk about absolute entropies. Okay, so just entropy itself, or S rather than delta S. That's in contrast to, say, internal energy E or enthalpy H, where for those we pretty much always talk about the change in those quantities, delta E or delta H. We don't generally talk about just this is the enthalpy of this stuff. Okay, but for entropy, we can actually do that because of this third law definition. So what does that mean practically? How do we work with these? If we look in thermodynamic tables, like the ones you've been looking in to look up heats of formation for things, probably if you've been doing problems on those. In addition to the heat of formation, you'll find another column which is labeled as S naught. That's the standard molar entropy for a substance, okay? The units on that are usually joules per mole per Kelvin. Okay, so that's the entropy in joules per Kelvin for 1 mole of that substance. If we had more than 1 mole, then it would have more entropy, right? Because entropy will scale with how much substance we have. That naught sign there, the degree sign thing, that again refers to our standard state being at nominally room temperature and pressure. Typically in the US at least, that's 25 degrees C and 1 atmosphere pressure, okay? Notice that the value for that S naught should never be equal to 0. Why not? Because it's measured at 25 degrees C, right? And the entropy would go to 0 if the temperature went to 0 Kelvin. 25 C is much higher than 0 Kelvin, obviously, and therefore the entropy values, we expect them to be positive. Just a little bit of disclosure here. If you were to scan down the entire table, you would probably come across a value here and there that are negative, okay? Which seems impossible with the definition that we're putting forward here. The things that show negative entropy values are always for ions in solution, and ions in solution require a different definition of the standard state because you can't have a crystal of, say, sodium plus ions, right? You can't make a crystal that contains only Na plus ions because the whole thing would have a positive charge and it would want to blow itself apart, right? We're not going to deal with those things, and so we will not encounter any entropies any S values that are 0. Now, delta S can be negative, right? But S itself, we will not encounter negative values for that. I only mention that because you could see them in the table if you were just to look through there. So the working form of this, if we want to calculate delta S for a reaction, by far the most frequent way to do that is with the equation that's on the screen now, right? Which just says delta S is the entropy of the products minus the entropy of the reactants. That's almost just the definition of what delta S should be, right? Because the products are what we have at the end, the reactants are what we had in the beginning. The end minus the beginning is our delta, okay? Since we can look up that molar entropy for every substance that's in our reaction, that says that we can find delta S for any reaction by just taking the sum of the entropies for the products minus the sum of the entropies for the reactants, with all those molar entropies just multiplied by what in the way the equation is written here are the N's. That's just the number of moles that are in the equation, okay? So what's going to happen there is my delta S, this thing is going to come out just in joules per Kelvin, because in here, my N's are going to be in moles, and my S's are going to be in joules. Joules, I don't know how that was a J. Joules per Kelvin mole. Okay. And so the moles will cancel. I'll be left with joules per Kelvin. The only difference between this and the equation you use for finding delta H is a subtle one. It's that here, this is S naught, the absolute entropy, and it is not delta S of formation. Okay, there's no formation reaction involved here. The other thing that you have to be a little bit careful here is that S naught is not equal to 0 for elements in standard states, okay? So if you look up the molar entropy of, I don't know, say N2 gas, it's not going to be 0, whereas the delta H of formation would be 0. Okay, that's just because of the difference in those two quantities, the absolute entropy versus the enthalpy change of formation. Okay, so if you've been doing delta H problems and you're used to seeing, say, O2 in your reaction and knowing like, oh, that one's 0, if you're doing delta S, you will need to get a value for that. Okay, so be on the lookout for that. That's a frequently made mistake. I'm going to do a quick calculation here just to illustrate how this works. This is a somewhat unusual reaction, which we'll talk about more in a later video. It can be used to separate nickel from other metals in ores, actually. But it has solid nickel metal reacting with carbon monoxide, the CO. It makes this product compound, which would be called nickel tetracarbonyl, in which the 4 CO molecules essentially all attach themselves to a nickel atom. The thing that's curious about that molecule is it's a fairly heavy molecule, but it is in fact a gas at normal temperatures and pressures. Okay, and so we'll come back to that reaction and an application for it later. For now, I'm just going to use the data that are on the screen right now to calculate delta H, which is a little bit of review of delta H calculations, and then delta S, in which we'll do the stuff we just did. Wherever I copied these from, I put on here this delta S naught at 298. That just means it's at 298 K, that 25 degrees C reference temperature, okay? Here's an example. Nickel is an element in a standard state, right? And so notice that where delta HF is 0 for the nickel, the heat of formation is 0, the entropy is not 0. It's relatively small. You can tell that the gases do in fact have much larger entropies there than the solid does, right? I said that when we first defined entropy, that gases would have much larger entropies. And here, looking at those values, you can see that's in fact true, right? Because I've got things in the hundreds for the gases and just about 30 for the solids. So there is a big difference there. Units, when you work with these things, you do have to be a little bit careful. Oh, that's not supposed to be an S. That's supposed to be an H. That doesn't make any sense the way it's written. Sorry about that. Delta H of formation, the heat of formation values in the table are in kilojoules per mole. The entropies are in joules per Kelvin mole. Okay, so when we work with both of these, you do have to be careful to make sure you get the units correct for the quantity that you're actually looking at. All right, let's do the calculation. I'm going to do delta H first. Where I can say delta H for my reaction should be equal to just the product. So that's the heat of formation for the product, which is the nickel carbonyl, minus the heats of formation for the reactants, and then I can put in the numbers, grabbing them from the previous slide or from my cheating notes over here. So this is 602.9 minus the nickel is 0, minus 4 times, and this one is minus 110.52. And if I multiply that out according to my notes, I get minus 160.8 kilojoules. Right? And again, my units there come out for kilojoules because the coefficients, the 4 here is the obvious one that has units of moles. The implied ones in front of the other numbers also would have units of moles to get me from kilojoules per mole for the actual heats of formation to just kilojoules, okay? Then delta S, I can say delta S should be equal to S naught for the product minus S naught for the nickel minus 4 times the entropy S naught for the carbon monoxide. Numbers for those, I get 410.6 for the product. The nickel is 29.87. These are just the numbers again that were on the previous slide. And then the CO, I get 4, and it's should be about 200, yeah, 197.56. When I sum those properly multiplied and all, I get minus 409.51. That's now in joules per Kelvin. Let's take a quick moment and check up on the signs for this stuff, okay? In the delta H, I have a negative delta H. What I've done is, it turns out if we looked at an actual Lewis structure for that nickel carbonyl, which is not one I would ask you to draw, but basically the triple bonds in the CO molecules all still exist. And what's really happened is the lone pair on the carbon has attached itself to the nickel. And so I've basically made bonds without seriously breaking bonds, at least in the CO part, okay? And so that being exothermic is at least somewhat reasonable. The one on the bottom, the delta S sign, that might bother you a little bit if you're not looking carefully, okay? It's true that we have solid and gas on the left, and we have only gas on the right. But when we say we want to use the gases to figure out what the sign should be, the correct way of thinking about that is to say the side of the equation that has more moles of gas will generally have the higher entropy, right? In this case, I turned 4 moles of CO into 1 mole of the nickel carbonyl, right? So I had 4 moles of gas on the left, and I have only 1 mole of gas on the right. So the fact that delta S is negative actually is reasonable and sensible there. What that means essentially is that in the product, because the 4 carbon monoxides are all attached to the same nickel atom, wherever that molecule goes, the 4 COs have to go there together because they're all attached to the same nickel. On the left-hand side, when I have 4 COs, they could be going to 4 separate corners of the box, right? And so there's a lot more ways to arrange them when those 4 CO molecules can move independently, as opposed to when their motion is correlated because they're all locked to that same nickel atom, okay? Those values, we'll actually grab those and I'll bring those back and use them in a future iteration example that will involve this same reaction.